The question is, could you do an example to show how to use the coordinate transformation equations for strains? Here's the problem that I have selected here. The components of the plane strain at a certain point with respect to a two-dimensional Cartesian coordinate system xy are these. Epsilon x is 0.03, epsilon y is minus 0.02, and gamma xy is 0.04. The first question is to determine the components of the strain with respect to a coordinate system which has been rotated 30 degrees counterclockwise from the xy coordinate system. The second question is to determine the principal strains and their directions. The third question is to determine the maximum shear strains and their directions. Finally, the fourth question is to compare and discuss the relative directions of the principal strains and the maximum shear strains. I copied the relevant coordinate transformation equation from another video. So what is given are the components of the strain with respect to this xy coordinate system, and we want to find the components of the strain with respect to this rotated coordinate system where the x prime axis has been rotated counterclockwise through an angle theta. These are the compact form of the coordinate transformation equations. There are four sections here. First, you define these parameters: epsilon average, little a, little b, and capital R by these equations. We have a little cautionary note here that in defining little b, we want to use epsilon xy, not gamma xy. Alright, so epsilon xy is gamma xy over 2. Once we define this parameter, then we simply use these three equations to find epsilon x prime, epsilon y prime, and epsilon x prime y prime, which are the components for the strain with respect to this rotated coordinate system. And this will help us answer the first part of the question. Next, these are the equations for finding the principal strains, epsilon 1 and epsilon 2. And we also calculate two angles to go with these principal strain, theta p and alpha p, but we don't know which one goes with what. So I have a comment on the next slide on that. Finally, we calculate the maximum shear strains by these equations. Here too, we calculate two angles, theta s and alpha s. The first comment here has to do with matching the angle theta p and alpha p with the principal strains epsilon 1 and epsilon 2. So what we do is we take one of these two angles, let's say theta p, and substitute that into the transformation equation for epsilon x prime. If epsilon x prime is calculated to be epsilon 1, then we know epsilon 1 goes with theta p. Otherwise, it's other way around. Comment number 2 here says we follow the same approach in matching the angles with the maximum shear strains. Let's answer the first part of the question here. First, we calculate these four parameters: epsilon average, little a, little b, and capital R. These are simply functions of these strains, epsilon x, epsilon y, and gamma xy. So we have the values here. All we have to do is to substitute these numbers into these equations and calculate values for these parameters. These are the values I got for these parameters. Theta is 30 degrees counterclockwise, and the coordinate transformation equations were derived for an angle in the counterclockwise direction. And therefore, theta to be used in this equation is plus 30 degrees. So just keep in mind that if the angle given was defined in the clockwise direction, then you should use a minus value of that. Alright, now it's a matter of substituting numbers into these transformation equations. So that's what I have done here, and the values that I'm getting are these. This is my epsilon x prime, and this is my epsilon y prime, and this is my epsilon x prime y prime. And if you do want to calculate gamma x prime y prime, all you have to do is to multiply this by 2. Here are the calculations that pertain to the principal strains. Here are the four parameters that we calculated in the earlier slide. Epsilon 1 is then calculated using this equation to be 0.037, and epsilon 2 using this equation is calculated to be minus 0.027. And here are the values of the two angles to go with these principal strains. So let's figure out which one goes with what. So here's what I have done. I took theta p and used that as theta in my coordinate transformation equation for epsilon x prime. The value that I calculated for epsilon x prime is exactly equal to epsilon 1. Therefore, this is proof that theta p goes with epsilon 1, and therefore alpha p, which is 109.33 degrees, goes with epsilon 2. So what exactly does it all mean? Well, this is what it means. Direction 1 here, which is oriented at 19.33 degrees counterclockwise from the original x-axis, is the direction of the principal strain 1, epsilon 1. So this is the direction for epsilon 1. The direction of epsilon 2 differs from this by 90 degrees counterclockwise. In other words, the direction of epsilon 2 with respect to this original x-axis is 109.33 degrees, which is the value of alpha p. So if you had a rectangular differential element like this, defined with respect to the directions 1 and 2, this element will deform with these principal strains. There will be no shear strains. Remember the definition of the principal stresses, right? The element is subjected to the principal stresses with no shear stresses on the faces, right? The same thing is true for the strains as well. So there is no shear strain with respect to these directions 1 and 2. Here is the analysis concerning the maximum shear strains. The magnitudes of the two shear strains are found by these equations. So I get values of 0.064 and minus 0.064. The two angles to go with these shear strains are these. Theta s is minus 25.7 degrees and alpha s is 64.3 degrees. Once again, to match the angles with the shear strains, we follow the same approach that we followed for the principal strains. And here I chose theta s for theta and went ahead and calculated epsilon x prime y prime, and that turned out to be 0.032. Now recognizing gamma x prime y prime is twice of that, we see that this is exactly equal to gamma max 1 divided by 2. And therefore gamma max 1 goes with theta s and gamma max 2 goes with alpha s. Here is the geometrical interpretation of these angles. Now let's try to answer the final part of the question, which is compare and discuss the relative directions of the principal strains and the maximum shear strains. This is what we got for the principal strains and this is what we got for the shear strains. If I now combine these two and plot the directions of the principal strains and the maximum shear strains in the same figure, this is what we get. The axes drawn in black are the directions of the principal strains and the axes drawn in purple are the directions of the maximum shear strains. This angle is 19.3 degrees and this angle is 25.7 degrees. If I add the two, I get 45 degrees. Since the angle between axis 1, the purple axis 1 and purple axis 2 is 90 degrees, this angle is also 45 degrees. In the similar vein, this angle is 45 degrees. So what we are finding is that the directions of the principal strains and the maximum shear strains are 45 degrees apart from each other. If you recall, this is exactly what we found in the case of stresses as well. The directions of the principal stresses and the directions of the maximum shear stresses were 45 degrees apart from each other.